The branch of geology called stratigraphy deals with the study of Earth's history as recorded in layers of rock. Earth records time by forming rock. Here at the Grand Canyon, that time is laid out like the pages of an open history book through the exposure of different layers of rock of different ages. But how do we read that history? It's not written in words. Instead, it's written in the language of rock. We need to be able to speak that language to interpret the history being presented here. In speaking the language of rock, we need to think about the different principles that guide our interpretation of stratigraphy, how we interpret the relative ages of rock layers, which are older, which are younger. There are several guiding principles to stratigraphy. The first is simple. It's called original horizontality. This means that sedimentary rock layers are initially formed in layers that are approximately horizontal. This reflects the deposition of sediment on some surface, namely a lake bed or seafloor or some other Earth surface. That surface is approximately horizontal, and so the layers start out horizontal. Any change in position from that original horizontality has to occur after those sedimentary rock layers were formed. Next principle is superposition. Superposition simply means that if the layers are not disturbed, they're still going to be in order. They're deposited in order from oldest layer at the bottom to youngest layer at the top. This is because there's no way to get younger sediment beneath older sediment. Sediment accumulates on the surface. The youngest sedimentary layer is the one that's on top, and layers get progressively older as you move down that sequence of layers. The next principle applies not to sedimentary rocks, but to other types of rocks like igneous rocks. You can get igneous rocks beneath older rocks, and this occurs when magma intrudes into the crust and then crystallizes, creating what's called a cross-cutting relationship. Our igneous intrusion would be younger than any rock it intrudes, and older than any rock it does not. In other words, for igneous rock to intrude, there has to be some rock there already to be intruded into. The same cross-cutting relationships can be applied to faults as well. A fault is younger than any rock layer it cuts across, and older than any rock layer it does not. In speaking the language of rocks, we also need to be able to recognize where there are gaps, where there are missing pages, where time was not recorded because rock was not being formed. These are called unconformities. Think of an unconformity as a gap in the stratigraphic record. There are three types of unconformities that form in slightly different ways. In other words, the presence of an unconformity indicates not only missing time, but a specific set of geologic events that occurred to form that unconformity, but were not recorded by the formation of rock. The first type is a nonconformity. This occurs when sedimentary rock layers directly form on or deposited on, overlie igneous or metamorphic rocks. This indicates that an erosional surface formed in those igneous and metamorphic rocks before new sedimentary layers were deposited. In other words, there's missing time between the sedimentary rock and the igneous and metamorphic rock beneath it. Otherwise, our sedimentary rock would be cross-cut by that intrusion, which shows signs of metamorphism because it would already have been there when the igneous or metamorphic activity occurred. The next type of unconformity is probably the easiest one to recognize. It's called an angular unconformity. This occurs when sedimentary rock layers that are still in their original horizontal position directly overlie rock layers that are tilted. How does an angular unconformity form? You deposit layers in horizontal position. Then you disturb those layers through a folding or uplift event. Those layers are now no longer in horizontal position. Then new layers that still remain in horizontal position are deposited on top of them. That contact between older layers, no longer horizontal, and younger layers, still horizontal, is the angular unconformity. So again, the angular unconformity represents not just missing time when no rock was formed, but also a specific series of events that took place during that missing time. Uplift and folding of older rock layers, erosion of those older deformed layers, and then finally time starts being recorded again when new rock layers deposit on that erosional surface. The last type of unconformity is called a disconformity. This occurs when you have a period of non-deposition, no time recorded by formation of rock, between sedimentary layers that are still horizontal. How does this form? Again, we have a sequence of sedimentary layers deposited, and then deposition stops. We stop forming rock, and we start eroding it away. We form an erosional surface. Finally, we deposit new sedimentary rock on top of that surface. The result is an irregular contact between our younger and older rock. Both layers are still in original horizontal position, but there's an irregular contact between them. You may also find fragments of the older rock within the younger rock, pointing to a period of erosion, a period of non-deposition, time not being recorded within that sequence. Finally, in thinking about the language of rock, we need to also be thinking about the processes that form different types of rock. In other words, in different environments, we lay down sediment and form rock with different characteristics. This is because rock and sediment reflects the processes of formation. Using our knowledge of the type of sediment that accumulates in different environments, and recognizing that type of sediment in different kinds of sedimentary rock, we can infer the conditions that must have existed at the time that layer was being formed. For example, the sediment deposited by glaciers is very different than the sediment that's deposited in deserts, which is very different than the sediment being deposited on tidal mudflats, very different than the sediment deposited out in the open ocean. Recognizing those differences and how they reflect different environmental conditions allows us to infer what the region must have looked like, what environmental conditions existed at the time a particular rock layer was being formed. So let's apply our knowledge of stratigraphy and unconformities and different depositional environments to the sequence of rock layers that has been exposed for our viewing by the erosion of the Grand Canyon. This figure shows a schematic illustration of the different rock types exposed in the canyon walls, and also the nature of their contacts, allowing us to infer the different types of unconformities that exist in this sequence. Using superposition and cross-cutting relationships, we see that the oldest rock layer here is the Vishnu schist, a metamorphic rock. That Vishnu schist was intruded by the Zoraster granite, because the granite cuts across the schist, but does not cut across the younger rock layers of the Grand Canyon Supergroup. So the first rock layer to be formed here is the schist, followed by intrusion of the granite. What tectonic setting is represented by metamorphic rocks like schist, and high silica felsic igneous rocks like granite. Well, those kinds of rocks form in a convergent tectonic setting. You make high silica magmas like granite in subduction zones. You form schist and other high pressure metamorphic rocks by mountain building and continental collision. So the Vishnu schist and the Zoraster granite represent a time when the Grand Canyon region was at a convergent plate boundary. Subduction followed by collision, forming high silica igneous rocks, and also resulting in metamorphism of those rocks, whatever rock existed there previously, into metamorphic rocks such as schist. Where can we find a similar tectonic setting to the one represented by the oldest rock layers exposed at the bottom of the Grand Canyon? Well, we identified that the schist and granite represent a convergent plate boundary, subduction and continental collision, forming igneous, high silica igneous and metamorphic rocks. We see the same types of rocks being formed today in the North Cascades. Subduction is occurring, high silica magmas are being made. At the same time, thick blocks of buoyant crust are being accreted to, colliding with North America, forming metamorphic rocks and a compressional mountain range. So at the time the Vishnu schist and Zoraster granite were being formed, the tectonic setting of the Grand Canyon region was similar to that of the Cascades. This same tectonic setting, collisional plate boundary, also existed earlier in the Appalachians, where similar types of rocks can be found. What's the next rock unit to form here at the Grand Canyon? Well, superposition tells us the next layer to form are the rock layers of the Grand Canyon Supergroup, consisting of a series of related rock types, sandstone layers that are very coarse, some shale layers, and also some intermixed mafic or basalt lava flows. We need to be thinking about what tectonic setting is represented by the formation of the rocks that belong to the Grand Canyon Supergroup. Well, basalt lava flows, coarse sandstones, and shales, this is inferred to represent a continental rift zone. Ancient North America collides with another continent during the time that the Vishnu schist and Zoraster granite were formed. A mountain range results. That mountain range gradually erodes, and eventually the continent breaks apart again. Breaks apart by the process of continental rifting. When that occurs, we have low silica magmas being formed by decompression, erupting on the surface as basalt, and then in that continental rift zone, where we have divergent tectonic stresses, we have subsiding basins subsiding along normal faults. It's in those basins that sandstones and shales may be deposited. Those sandstones and shales, well, the sandstone is coarse because it's close to the sediment source, the rising fault block mountains on the other side of those normal faults. And at times, those basins may support lakes in which shale is going to be deposited. A similar tectonic setting to the one that existed in the Grand Canyon region at the time the Grand Canyon Supergroup was formed can be found today in the Basin and Range Province and Rio Grande Rift of the western U.S. Here, divergent tectonic stresses are producing fault block mountain ranges, subsidence along normal faults. Coarse sands are accumulating because we're close to the sediment source, the uplifted fault blocks on the other side of those normal faults. In some places, large pull-apart basins or grabens are formed which occasionally support lakes, in which shale and other fine-grained sediment made of clay is being deposited. And of course, the stretching and thinning of the crust is accompanied by low silica basalt lava flows. Again, using our knowledge of where these different rock types form and why they might be found together in a set of related units allows us to infer what the tectonic setting and geologic environment of the Grand Canyon region was at the time the supergroup units were being formed. It was a continental rift zone. The remaining part of the sequence, the upper part of the Grand Canyon, consists of flat-lying sedimentary rock layers. Superposition dictates that the layers on the bottom are the oldest, the layer on top is the youngest. In other words, as you move up towards the rim of the canyon, you're encountering younger rock. Conversely, as you hike into the canyon from the rim, you're hiking back through time. You're encountering older and older rock as you descend deeper into the canyon. What is the tectonic setting represented by the flat-lying sedimentary rock layers of the upper Grand Canyon? Well, what does a continental rift eventually grow into? Well, if the rifting process continues, a new divergent plate boundary develops, a new mid-ocean ridge, an ocean ridge that grows by seafloor spreading. What happens to the trailing edges of the continental crust? Continental crust that broke apart during the rift stage. It eventually cools and subsides and becomes what's known as a passive continental margin, and thereby becomes a place for thick layers, for a thick sequence of sedimentary rock layers to accumulate on that passive margin. So the rock layers of the upper Grand Canyon represent sedimentary rock layers accumulated on a subsiding passive margin as our ocean basin grows, first by rifting, represented by the Grand Canyon Supergroup, and then by seafloor spreading, while the former rifted edges of the continent become a passive continental margin. Well, as you can see, there's a variety of different types of sedimentary rock layers represented in the sequence deposited on the passive margin. We have sandstones, we have shales, we have limestones, different types of sedimentary rocks forming in different types of depositional environments. So what are the depositional environments represented by each of these rock types? What kind of environment does sandstone form in? What does the size of the crossbedding tell us about the environment in which that sandstone formed? What kind of environment does shale form in? What kind of environment does limestone form in? By recognizing the different environments represented by these different rocks, we can infer how the environmental and geologic conditions changed in the Grand Canyon region as this sequence of rock layers was deposited on the passive margin. Well, the oldest of the passive margin layers is the one directly above the supergroup called the Tapeats Sandstone. This is what the Tapeats Sandstone looks like. You can see that it has these angled features within otherwise flat-lying sedimentary layers. Those angled features are called crossbeds. They also tell us something about how that sand was deposited to eventually become sandstone. Crossbeds, small-scale crossbeds, form when a ripple migrates across a bedding surface. Sand grains are pushed up and over that ripple and then deposited again. In other words, the ripple migrates in the down current direction, forming these angled features called crossbeds. In the case of the Tapeats Sandstone, crossbeds are angled the opposite way, indicating the current direction. In this picture was right to left. You can see the same type of environment if you visit the beach. lots of sand, a relatively high energy environment, close to the shoreline, high energy environment needed to deposit sand-sized grains, and the high energy is also reflected in the formation of ripples and crossbeds. So the Tapeats Sandstone is interpreted as representing a sandstone layer deposited either at the beach or very close to the shoreline on that passive margin. The next layer to be deposited on the passive margin sequence is called the Bright Angel Shale. Shale is a fine-grained, clay-sized sedimentary rock. You can see that those clay grains are being deposited in very thin layers that are more or less horizontal. To get these fine clay-sized grains to deposit, you need a low energy environment. The water has to be deeper. You need to be farther offshore. That indicates that sea level rose at this location. As sea level rose, the Grand Canyon region found itself farther from the shoreline. Sea level rise moves the shoreline away from the Grand Canyon region and puts the Grand Canyon region in deeper water, farther offshore. The environment has changed from near shore to offshore, high energy to low energy. Sediment being deposited changes from sand to clay. That shows up as a change from sandstone to shale. In other words, whenever the depositional environment changes, the type of sediment and sedimentary rock that we form changes. In this case, the sea level rise at this location has moved the region away from the shoreline, put it into deeper water, changing the type of sediment from sand to clay. Sandstone to shale is now being formed. The next layers to be deposited are the Mauv and Redwall limestones. Limestone is a chemical sediment made of the mineral calcite, calcium carbonate. In what environment does calcium carbonate get deposited? Well, it deposits in warmer, subtropical water. So the presence of limestone layers in the Grand Canyon region is telling us that at the time those limestone layers were formed, this area was closer to the equator than it is today. The environment would have been similar to that of the Bahamas today. Shallow tropical sea, calcium carbonate is less soluble in warm water, so it's being deposited as a chemical sediment. Limestone is being formed. Due to continental drift, the Grand Canyon region later moved northward, away from the equator. But during the time it was a passive margin, and forming these layers of limestone, we were closer to the equator at this location. One of the younger layers in the passive margin sequence is the Coconino Sandstone. Coconino Sandstone is a little bit different than the Tapeats Sandstone, farther down and older, because it has large crossbeds that are on the order of meters in size. Those large crossbeds indicate sand deposited as dunes. In other words, in an aeolian or wind-dominated environment. Dunes are depositional features formed by wind action. And just like you form ripples, just like forming crossbeds and ripples, you also form crossbedding in dunes. Only the scale of that crossbedding is much larger. Here we see modern dunes. Here we see dunes that have been cemented by groundwater flow, which has laid down a chemical cement between those sand grains, preserving the crossbeds. And then on the right, we see the Coconino Sandstone. With its preserved crossbeds. Large crossbeds indicating deposition of that sand as dunes. Those might have been beach dunes, or they might have been dunes in an arid or desert-like environment further inland. Either way, Coconino Sandstone represents sea level fell. Remember, we had been making shale and limestone, water offshore. Sea level fall means the Grand Canyon region is now above sea level, depositing sand in an aerial or aeolian environment where wind, rather than water, is the primary driver of sand movement and deposition. In reading this history, told by the layers exposed by erosion of the Grand Canyon, we also have to watch for time periods when rock was not formed. Periods when time was not recorded because no rock was being made. Those are the unconformities. And the Grand Canyon sequence of layers represents examples or contains examples of all different types of unconformities. There's a wide range in ages of rock seen at the Grand Canyon, from about 1.7 billion years old to about 300 million years in age. In other words, Permian to Precambrian in age. Permian, Precambrian referring to intervals of geologic time. Wide range of ages, but only a small fraction of time is actually recorded by rock. Again, because some of these unconformities last hundreds of millions of years, representing times when rock was not being deposited because of a change in tectonic setting. During that time, Vishnu, Schist, Zoraster, Granite, convergent plate boundary, mountain range was formed. It took a long time to erode those mountains away till we could start making sediment again. By that time, we now have a divergent setting, a continental rift zone. The Grand Canyon Supergroup is formed. Then there's another unconformity that follows. Why? Because the rifting process leaves the area elevated as the new ocean grows between the now fragments of a continent. That area has to cool and subside, drop below sea level before it can start forming rock again, before sedimentary rocks can start being deposited. Once that happens, the area has completed its transition from continental rift to passive margin. And we start making sedimentary rock layers. But sea level change on that passive margin means that sometimes the area was above sea level, no rock was formed because we were above sea level at that time. Other times it was below sea level and rock was being formed. But what are the different types of unconformities present in the sequence? Well, schist and granite are igneous and metamorphic rocks. The Grand Canyon Supergroup contains basalt lava, an igneous rock, but it also contains sandstone and shale, sedimentary rocks. So we have a nonconformity present between the schist and granite and then the rock layers belonging to the Grand Canyon Supergroup. That nonconformity, this particular one, is sometimes called the Great Unconformity because it represents a very long period of time, nearly 1 billion years, representing the time it took for this area to go from a collisional plate boundary with a mountain range to a divergent plate boundary with pull-apart basins from continental rifting. between the Grand Canyon Supergroup, whose layers are tilted because they're formed by sinking of a fault, subsidence of basins along normal faults, we have an angular unconformity between the tilted Grand Canyon Supergroup and the flat layers of the passive margin. And then within the flat line layers of the passive margin, we find examples of disconformities, periods of non-deposition, due to low sea level. In other words, at times, the Grand Canyon region was flooded by high sea level, causing sediment to be deposited at this location. At other times, the sea would retreat, the area would find itself above sea level, and rock would generally not be formed as a result. Instead, erosion would occur when the area was above sea level, resulting in erosional surfaces or disconformities within the passive margin sequence. Here's a closer look at that nonconformity. Here we have metamorphic and igneous rocks with flat-lying sedimentary rocks directly on top of them. That contact, the nonconformity, represents a period of missing time during which erosion was occurring. The mountain ranges that were formed by the metamorphic and igneous activity were being eroded away, leveled by erosion, which took a long period of time, approaching 1 billion years. Once the region was reduced to near sea level, sedimentary rocks could start forming again. Here's a closer look at the angular unconformity. Below it, the rock layers of the Grand Canyon Supergroup, representing sedimentary rocks and basalt formed in a continental rift zone. Above it are the flat-lying layers deposited on the passive margin. The contact between the two, between our tilted and flat layers, is an angular unconformity. That unconformity represents a period of time when our elevated trailing edges of the continent cooled and subsided below sea level and became a passive margin. Not until they fell below sea level could sedimentary rock layers start forming again. During the rift stage, space to accumulate sediment occurred as a result of subsidence in these basins along normal faults. Once the faults die out, the basins fill with sediment, and then we stop making sediment, stop forming rock. During that time, the whole area finds itself farther and farther from the ocean ridge, which is where the plate boundary is now, gradually cooling and subsiding to form a passive margin, dropping below sea level and allowing the deposition of sediment to resume, forming the flat-lying layers on the passive margin. And within our flat-lying layers of the passive margin, we find several irregular contacts or erosional surfaces, representing periods of time of low sea level. Area was well above sea level as a result, and no rock was being formed. Instead, we have erosion of already existing rocks occurring. And this shows up as an irregular contact between those rock layers, and also fragments of the older rock layer incorporated within the younger rock layer. So looking for signs of a disconformity, require close inspection of the contact between sedimentary rock layers and the nature of that contact. Is it flat, in which case deposition was continuous, or is it irregular, in which case there's a period of missing time here? Let's sum up what we've learned so far. Let's read the sequence recorded in the history of these rock layers exposed by the erosion of the Grand Canyon. We start with the Vishnu schist, the oldest rock layer present here, a metamorphic rock formed at a convergent plate boundary, intruded by the somewhat younger but still very old Zoraster granite, a high silica igneous rock, pointing to the fact that this convergent plate boundary was a subduction zone. Then we have a long period of non-deposition, a long unconformity, a non-conformity, representing the period of time it took to erode away the mountain ranges produced on that convergent plate boundary. By this time, the area becomes divergent. A rift zone develops, forming the related rock units of the Grand Canyon Supergroup, including basalts, coarse sandstones, and shales. The basalts come from the low silica magma that accompanies continental rifting. Divergence at the surface decompresses the mantle, allowing low silica magmas to be formed and reach the surface. Sandstones are coarse, reflecting the fact that they're deposited close to the source of the sediment. Remember, during the rift stage, you're breaking the crust up along normal faults. Some blocks go up, those become mountain ranges. Other blocks go down, they become basins. The basins are where sediment is being deposited. Alluvial fans, coarse sediments like sandstone and conglomerate. And at times the basins would support lakes where shale may be deposited. Similar environments can be found today in the Rio Grande Rift of New Mexico and Texas, and also in the East African Rift. Then another long period of non-deposition follows, another unconformity. This is an angular unconformity because the supergroup layers are tilted, the younger layers above them remain flat. This angular unconformity represents the time it took for our elevated sections of the continent to cool and subside, to move far enough away from the new divergent plate boundary to cool, subside, drop below sea level, and become a passive margin. And on that passive margin, a variety of depositional environments existed at different times, depending on relative sea level at this location. When we're close to the shoreline, we're depositing a coarse sandstone, we're depositing a coarse sedimentary rock sandstone in a relatively high energy environment, shallow water, wave action, and ripples, forming the Tapeats Sandstone with its small crossbeds. Sea level rises, the environment becomes farther offshore, deeper water, and we now deposit the Bright Angel Shale. Presence of the limestone layers represent shallow tropical seas where calcium carbonate is being deposited. The Supai group contains shale and sandstones, representing an environment where we're once again relatively close to the shoreline, at times depositing shale, at other times depositing sandstone. Hermit Shale, deep water environment farther offshore, produced by, again, sea level rise, moving the coastline away from the Grand Canyon region, depositing that shale layer. Coconino Sandstone, sea level has fallen. We're now depositing sandstone, coarse-grained sediment again, has large sand grains, or large crossbeds, I should say, representing deposition as dunes in a subaerial or aeolian environment dominated by wind rather than water. Finally, the youngest layers are the Torweep and Kaibab limestones, representing one final return of the sea, deposition of calcium carbonate in a shallow warm water environment. So the rock layers of the Grand Canyon region represent deposition in a variety of settings. Ancient rock of the crust, older Rift Valley strata, and then the younger passive margin layers. This entire sequence of rock has been uplifted in recent geologic time, and that provided the Colorado River the power to erode through those layers. As erosion occurred, the river is cutting into progressively older and older rock, exposing them for us to study and piece together the history of this region as told by the rock layers exposed in the walls of the Grand Canyon. So in summary, Grand Canyon is not just a hole in the ground, rather it's a window. It's a window allowing us to look back through time at progressively older rock layers as we move deeper into the canyon.